Magnetic field of a bar magnet. The purpose of this lab is to explore the correlation between the observable distance and magnetic field strength using a bar magnet, and to further understand the Biot-Savart law both on and off axis. We will then model this computationally using GlowScript and VPython. The main physics principles that we will be using in this lab are the Biot-Savart law, as shown as the first equation on the right, which describes the magnetic field generated by a constant electric current. Secondly is bar magnets, which are magnets that have a north and a south end and act as magnetic dipoles. Next, we use the concept of magnetic field superposition, which is that the net magnetic field is due to the summation of all magnetic fields. Lastly, the distance dependence equations as shown to the right, which we will use to calculate a value for n, or to derive a value for n. This experiment resulted in a magnetic field proportional to the distance to the negative 3.13 power, and the dipole moment equal to 2.52 joules per Tesla. The conceptual model models a bar magnet as shown to the right. The observed field depends on the dipole moment, which points north to south, and the observation vector r. These quantities were all expressed in the Biot-Savart law as seen previously. We make the assumption that r is the only value that is not assumed to be a constant. So we can express the magnetic field as a function of constant k times r to the nth power, where we will expect n to be equal to approximately negative 3 in an ideal scenario. The first part of the procedure is to determine the direction of magnetic north, which is crucial for the experiment. To do this, we will lie the phone flat on a surface and rotate it until the x component, according to the magnometer app, is equal to 0. We then set the meter stick up so that the stick is perpendicular to north. Next, we slide the phone perpendicular to the meter stick in both the x and y direction to locate the magnometer of the phone. Lastly, we move the phone at a variety of distances along the meter stick on axis at a 45-degree angle and record these values. So the data for the on-axis measurements for the average R, average mag fields in the x direction, and the derived values for the natural log of R and the natural log of the magnetic field in the x direction are shown. To get a value for n, we will do a linearization and linear regression by plotting the natural log of the magnetic field in the x direction against the natural log of r. And use the distance dependence equation to get a linear equation as shown. The graph of the linear regression is shown from the slope equation, negative 3.13x plus negative 14.5 to get n and k. N is equal to negative 3.12, which is a percent error of 4.3 from the expected value of negative 3, and a k value of 5.04 times 10 to the negative 7, as derived as shown on the slide. As shown in the diagram, we position the magnometer of distance d perpendicular from the axis and then measure the magnetic field as we did in the first part. We will then account for the Earth's magnetic field by subtracting it from the y component of the magnetic field. From this, we get the following data values. The average distance d perpendicular is 0.182 meters. The average net magnetic field is 0.0001763 teslas. And the measured net magnetic field vector is 1.6 times 10 to the negative 4 teslas in the x direction, 5.4 times 10 to the negative 5 in the y, and 3.8 times 10 to the negative 5 in the z directions. Now that we have this data, it is time to model the magnetic field using GlowScript, as shown in the code in the next two slides. First, lines 55 through 60 define the observation locations that we will be using. Next, lines 64 through 66 show a sample calculation of the magnetic field, which we will do for all observable locations. Then, in line 110, we plot a 3D arrow of the magnetic field vector for the off-axis point, which will be defined in the next slide. The conceptual model and calculated values are shown at the bottom of the slide. For the second part of the GlowScript code, we calculate the magnitude of the net magnetic field. Lines 33 through 37 are defining a method that calculates the magnetic field using the Biot-Savart law. Lines 103 to 111 use d perpendicular to create the 45-degree vector that was plotted in the last line of the last slide and calculates the computed magnetic field. We see from this that we get a pretty different value than the measured, which was 1.6 times 10 to the negative 4 teslas in the x direction, 5.4 times 10 to the negative 5 in the y, and 3.8 times 10 to the negative 5 in the z. Whereas the computed from Python and GlowScript is 7.39 times 10 to the negative 6 in the x, 2.21 times 10 to the negative 5 in the y, and 0 in the z directions. For the first question, if the experiment was not oriented to magnetic north, then the magnetometer readings all would have been inaccurate because they would be skewed in the direction of magnetic north, therefore making our calculations for k, mu, and n inaccurate. For the second equation, if we were to run the experiment again with two identical magnets together, then the direction of the magnetic field would remain the same, but the magnitude of the field would significantly increase. Thank you.